Hi, today I'd like to introduce you to a quantity called charge and the force that different charged objects create on each other. Now, this force, called the electrostatic force, is one of the four fundamental forces, and gravity is one of those. The strong nuclear force is the third, and I think it's the weak nuclear force is the fourth general major type of force. And the electrostatic force is the force that's responsible for most of the forces that we deal with. When you push on an object or pull, when there's tension, when there's friction, all those are examples that at their heart are created by the interaction of charge. And there's two different types of charge, positive and negative charge, and ultimately these come from the number of protons and electrons that matter has. A proton is defined to have the smallest unit of positive charge, and electrons are defined to have negative charge. And these charges interact with each other, like the poles on a magnet, for instance. The north pole and the north pole of magnets repel each other. In a similar way, a proton, a positively charged object, and another positively charged object will repel each other, and electrons tend to repel each other. But if you get a proton near an electron, they'll attract. Or if you have just any old positively charged object near something with a negative charge, they tend to attract each other. And this electric force, the one that's responsible for pushing, pulling, tension, the thing that keeps your body together, that holds all of your atoms together, this electric force is significantly stronger than gravity. In fact, the gravitational force, you can pretty much ignore it in day-to-day life except for when you start to have really massive objects like the Earth involved. Now, a little more about the quantity of charge. As I mentioned earlier, protons and electrons, they have the smallest unit of charge possible. And typically when you're talking about the charge that an object has, we're interested in the net amount of protons or electrons that it has. If you were to count up all of the protons in all of your atoms and count up all of the electrons in all of your atoms and compare those two numbers, most of the time they're basically equal. And so most objects have essentially zero charge, but occasionally some electrons might wander away and get transferred from one object to another. That can happen if you, say, rub a balloon on your hair. Usually you'll lose a few electrons from your body and they'll get put onto the balloon. And then the balloon has a negative amount of charge on it. And that's because it has more negatively charged electrons than it has protons. So that is one of the units, is just the number of electrons or number of protons. That's when you use the E. But that's not the standard unit, because typically we don't talk in terms of that many. It's just that's too small of an amount of charge. So the standard unit for charge is what's called a Coulomb. And a Coulomb is defined to be 6.24 times 10 to the 18. That's, I think, 6 billion protons. If you have that many protons, then you've got a Coulomb's worth of charge, and 6 billion electrons would be a negative Coulomb's worth of charge. Now, unfortunately, while an electron or a proton, the fundamental charge as it's sometimes called, while that's too small to be practical, a Coulomb is really too big to be practical. Most things have very few Coulombs, and I mean, like, well, down here, typically a more household amount of charge that you might be able to put on, say, a balloon by rubbing it or something like that, might be on the order of micro Coulombs, which is times 10 to the negative 6. You might see the mu symbol. Mu c means microcoulombs, or nanocoulombs, which is billionths of coulombs. This here, 1e, this unit conversion is the same unit conversion as this. It's just the other way around. this says that 1e, the charge of one electron, is 1.6 times 10 to the negative 19th coulombs, and that's the reciprocal of, if you have this many protons, that's equal to 1 coulomb. I think traditionally this conversion factor is taught more often and memorized, and I know that that's in the back of our physics books. So another unit that's worth mentioning but not too often used is a Faraday. That, if you've taken chemistry, you've probably learned of this huge number, which is a mole. A Faraday is if you have a mole's worth of excess electrons. It never really caught on, though it made sense to me, I think, to use it. And then amp hours or amp seconds is another unit of charge, and that has to do with current. I'll briefly talk about current a second now, but we'll dive into that in another video in a few weeks. But when charge gets transferred from one object to another, that's because usually electrons are moving from one object to another. Protons usually are too stuck in the atoms to move around and to be transferred from one object to another. So typically electrons move. When charge moves from somewhere to somewhere else, that moving of charge is called current. Current uses the symbol I, usually a lowercase I, and that's just defined as the amount of charge that moves past a location in a given amount of time. So change in charge divided by change in time. The unit that current is measured in, you've probably heard before, that's measured in amps. And when you've got a current of 1 amp, that means 1 coulomb's worth of electrons are marching by every second. So I don't have any examples of currents. A quick Google search could probably come up with a whole bunch of typical currents that you see in household equipment and in electronics and so forth. Now, the real meat of the lesson today is the force, the interaction between charged objects. And that interaction, that calculation can be made using this formula. The K in this formula is just a number, 9 times 10 to the 9th. And then the charge is the charge of the two objects involved, and then the distance between them squared. So one thing to note is the inverse square principle that's involved here with the distance. What that means is that as objects get closer together, the force that exerts between them will increase. And specifically, if you were to, say, cut the distance in half, so divide by 2, that actually quadruples the force. And if you were to cut the force by a factor of 10, that increases your force by a factor of 100, again because of the squared. If you double the distance, you reduce the force by a factor of 1/4, not 1/2. So anyway, a couple example calculations. Two charged objects are listed. They're separated by 1.4 meters. What's the force that acts between them? So pretty simple application of the formula. Simply plug in our numbers. K is the number 9 times 10 to the 9th. And then the charges are listed here. This is in essentially microcoulombs, 3 microcoulombs, and this is I think 40 microcoulombs. So this is household amounts of charge you might be able to put on objects. And we'll put in the numbers here. 4 times 10 to the negative 5th. That's our first charge, and 3 times 10 to the negative 6th. And then the distance between them is in meters. So the standard units for each of these is coulombs and meters. And I can calculate this. So a lot of times I will take the number K, that's 9 times 10 raised to the 9th, and store that into the letter K. I think that's useful, and I don't have to remember that number. I can just type in K in these formulas. So K times 4 times 10 raised to the -5th, and 3 times 10 raised to the -6th, and then divide by 1.4, I guess I don't need parentheses, 1.4 squared, and that gives us 0.55, and since this is a force, that would be in the standard unit of newtons. So these two objects, maybe they're balloons you rubbed on your head, separated by 1.4 meters, might feel a force of 0.55 newtons. I guess that's a little much because that's half an apple and they're quite a ways away. I normally don't feel that much attraction with balloons that far apart, but if you brought them closer, maybe. So maybe these charges are a little too high. Anyhow, another calculation. Let's suppose we have two objects and we put an entire Coulombs worth of charge on them. I say that with such enthusiasm because a Coulomb, as I mentioned earlier, is a lot of charge. Let's try to figure out exactly how much charge that is. So I get two balloons. They each have a Coulomb's worth of charge on them. I want to know when they will repel each other with a whole apple's worth of force, 1 newton's worth of force. So you can use the same equation, but here we know the amount of force. Let me write it a second, then I'll start filling in some things. Here we know the amount of force we're interested in is 1 newton. K is the constant, 9 times 10 to the 9th. The charge we put on each balloon is 1 Coulomb, and we're interested in the distance between them squared, or in the distance between them. To solve this, I like to cross multiply. You didn't know that this was over 1, but you could write it that way. And then this, so r squared is, this multiplication is essentially just k, 9 times 10 to the 9th. So the distance between them is the square root of k, which is square root of k, 94,868. That's a standard distance of, or standard unit of meters. So 94,000, that'd be roughly 94 kilometers. And if my conversions are right, that's roughly 60 miles away, because 100 kilometers per hour is usually 60 miles per hour. So what that suggests is if you have some objects with a whole Coulomb's worth of charge, then when they are still 60 miles apart from each other, you could feel a repulsion of a newton, about an apple's worth of force. So that suggests to me, since I've never felt that much with with static electricity sorts of forces and repulsions and so forth, that I've probably never came even close to a whole Coulomb's worth of charge. Let's suppose, again, ridiculous, but let's suppose we could take those Coulombs and bring them not 60 miles apart, but let's bring them in the exact same room and push them towards each other because they're repelling each other. They're both positively charged. Let's say we can push them together and bring them within a whole centimeter of each other. How much force would that take? How hard would it be to push to hold those together? Now this is just an application of the formula straight up. We'll put in the K, a Coulomb times another Coulomb. The distance between them is 1 centimeter. The standard unit for distance is meters, so I do need to convert that, write that. A centimeter is 0.01 meters. So put that in there, squared. We'll calculate this. K times 1 divided by 0.01 squared. (9e13). That means 9 times 10 to the 13th, or 9 and 13 zeros. Let's see here. I think I got that right. 90 billion? Trillion? I'm not quite sure. Newtons. Or basically, no, you can't bring a Coulomb next to another Coulomb's worth of charge. It's going to be too difficult. So, anyway, there's an example of charge, some calculations, and just a brief idea of how much charge a Coulomb is. Typically, a bolt of lightning usually transfers about 15 coulombs worth of charge from cloud to sky, or from cloud to ground, or back up again. So, thanks for watching, and tune back in again tomorrow as we talk about electric fields.